Hello there, and welcome to Fall Asleep to Astronomy. I'm glad you've wandered into this little pocket of quiet tonight. Outside, our planet turns through the dark as it always has, but far beyond the clouds, a small visitor from deep space is passing through an interstellar object called 3IATLAS. In a few short nights, around December 19, its path and Earth's story will briefly cross, and a simple question has been echoing in many minds. What will really happen when it does? Tonight, we'll sit with that question gently. We'll follow 3IATLAS from the cold between the stars to the warm blue world we call home, and trace what the physics actually says. No drama, just a calm, careful look at how close, how bright, and how safe this encounter will be. If this kind of soft, honest stargazing helps you unwind, a quiet like and a gentle subscribe help others find their way here too. When you're ready, we'll drift into the story together, unhurried and warm. December 19th, 2025 sits on the calendar like any other date, small and quiet. Yet folded inside that day is something almost no one who has ever lived has seen with clear eyes. A confirmed visitor from another star system passing through our part of space, close enough for us to measure its every move. Out of all the generations that have watched the sky, only 3 have shared their nights with such a traveler. You happen to be here for one of them. Astronomers call it 3IATLAS. The name sounds technical, but you can think of it as a little piece of ice and rock that was born around some distant sun and then thrown out into the dark. Right now, it is rushing through the inner solar system at tens of thousands of miles per hour, glowing softly as sunlight wakes up the ices on its surface. It sheds gas and dust the way comets do. Yet the way its path curves and its speed changes does not quite match what those gas jets should be able to do. Under the calm numbers sits the sense that something about it is off by a small but stubborn amount. In a few short weeks, the path of this object and the path of Earth's orbit will come very near one another. It will not sweep past the moon in any dramatic way, but in the wide language of space, it will be close, on the order of a few million miles. That is far beyond the reach of human senses, yet close enough that space agencies and observatories across the world have quietly turned their instruments toward it. Satellites above the atmosphere and telescopes on dry mountaintops are following a faint dot that moves a little each night, collecting every photon they can. The story of how we came to know it starts earlier, on a quieter night, October 13th, 2024. On that date, an automated survey looking for near-Earth objects took a set of images of a small patch of sky in the constellation Serpens. Among the sprinkled stars, one point of light was slightly smeared, shifted just enough between exposures to give itself away as something moving. At first, that motion looked like the routine trace of a new comet. It was logged, labeled, and passed along for follow-up. Within 2 days, after more measurements and some careful calculations, the picture changed. When astronomers plotted its positions and fit them with an orbit, the curve they saw was not a closed oval like most comets follow. It was open. The object was traveling at about 31 kilometers per second relative to the Sun, fast enough that our star's gravity could bend its path but never capture it. It would swing in once and then be gone, never to complete a second loop. That kind of path, a one-time swoop rather than a bound orbit, is what we call hyperbolic. In simpler terms, it marked 3IATLAS as a visitor, not a native. That realization put it into a very small family. In all the time humans have been watching the sky carefully, We have cataloged millions of objects that belong to the Sun: asteroids, comets, bits of debris left over from the making of planets. But interstellar objects, pieces of other systems passing through ours, on their way somewhere else. Number only 3 that we can say with real confidence. The first, seen in 2017 and named Oumuamua, slipped through so fast that by the time we recognized its path as interstellar, it was already on its way out. The second, 3I, Borisov, appeared in 2019 and behaved much more like a normal comet, sprouting a tail and obeying most of the rules we knew. 3IATLAS lives somewhere between those stories. Like Borisov, it clearly gives off gas as it warms. When scientists split its light into a spectrum, spreading it into colors the way a prism does, they see the fingerprints of ordinary cometary ices: water vapor, carbon dioxide, carbon monoxide. There is nothing there that screams of something impossible or artificial. Yet when they take that information and ask a practical question, how much should these jets of gas push on the nucleus, and how should that affect its orbit? The answer comes up short. The object is changing its speed and direction in a way that is roughly 15% stronger than the outgassing alone would predict. For a typical comet, that sort of calculation is comforting and precise. You imagine the surface as dotted with tiny vents. As sunlight warms each patch, gas escapes and acts like a weak thruster, giving the nucleus a slight nudge. Add up all those nudges over weeks and months, and you can forecast how the orbit will shift. With 3IATLAS, the observed shift is just a little too large. The rocket is firing harder than the fuel we see would normally allow. If that rings a bell, it is because we heard a similar note with Oumuamua. That object also picked up a small, unexplained acceleration as it left the inner solar system. Scientists proposed many gentle, grounded ideas. Maybe its shape gave sunlight more surface to push on. Maybe it was shedding gas in ways too subtle or uneven for us to detect clearly. A few voices wondered out loud if it could be something like a light sail, a thin sheet driven by starlight, though most of the community treated that idea as an interesting but unlikely speculation. Even so, the core discomfort remained. Our simple models did not capture every detail of its motion. Now, as 3IATLAS shows a similar mismatch between theory and reality, that discomfort returns. When 2 out of 3 known interstellar visitors behave in ways that refuse to fit neatly, it suggests one of 2 things. Either the physics of these ejected bodies carries subtleties we have not yet learned to account for, or the population of objects wandering between stars is more diverse, stranger, perhaps than the small, icy families that circle our own Sunday. Both possibilities tug at the edges of what we thought we understood. Behind those questions lies an older part of the story: how such an object is made and set loose in the first place. Picture a young planetary system forming around a newborn star. Disks of gas and dust swirl, clump, and collide. Embryo planets and giant worlds move through that disk, their gravity stirring it like spoons in a thick soup. Small bodies of ice and rock are tugged this way and that. Some fall inward and vanish into the star. Some settle into long, cold orbits far away. And some, after an especially close pass by a massive neighbor, are flung outward with so much energy that they escape entirely. 3IATLAS is almost certainly one of those exiles. Long ago, somewhere in the general direction of the constellation Aquila, it likely shared an orbit with countless other fragments around a distant sun. Then gravity changed its mind. A near encounter with a growing planet, or a series of overlapping tugs, pumped more and more speed into its motion. Eventually, its path did not close anymore. It climbed out of its home system's gravity well and into the galaxy at large, carrying its frozen cargo with it. From that point on, the story becomes simple and very long. It coasted through interstellar space, where the distances between stars are so vast that, for millions of years, it could travel without ever coming close to anything solid. The space between stars is not completely empty. There are thin wisps of gas, stray dust, grains, and bursts of radiation from flares and ancient explosions, but it is quiet enough that an object the size of a small mountain can drift almost unchanged for ages. That 3IATLAS still has ices to lose now, still grows a coma and faint tail when warmed, tells us that either the journey was not as destructive as it could have been, or that the journey itself may be shorter in cosmic terms than we first imagine. Eventually, our sun's gravity reached out to it, almost by accident. As it passed near the outskirts of our system, its straight-line path bent inward a little, then a little more, until it was falling toward the inner planets on a one-time swing. For a long while, we knew nothing about it at all. It was just one more nameless stone in the deep dark, following a curve that happened to cut across our part of space. Because of the direction it came from, we were always going to learn about it late. For much of its approach, 3IATLAS lay close to the blinding line between Earth and the Sunday. From the ground, that region of the sky is washed in scattered daylight and glare. Telescopes, designed to sweep for faint, moving points, avoid it, much as our eyes avoid staring straight into the light. Only when the geometry shifted and the object moved out of that bright strip did it step into the darker backdrop, where surveys could finally see it. By the time that happened, it was already well inside the solar system, on its inward rush. Once enough measurements were taken to define its orbit clearly, astronomers calculated how close it would come to Earth's path. The answer, about 0.027 astronomical units, or roughly 2.5 million miles, carries two very different feelings depending on the scale you hold in your mind. Compared to the Moon's average distance of about 239,000 miles, it sounds reassuringly large, 10 times farther away. Nothing about your everyday life will notice this passage. On the scale of the solar system, though, this is an astonishingly near miss. Space agencies consider anything that passes within 0.05 astronomical units, a bit under 5 million miles, to be a close approach. 3IATLAS will skim by at just over half that threshold. In the vast emptiness between planets, where most objects never come near one another at all, a gap of a few million miles is like two ships passing within a few body lengths in an otherwise empty ocean. There is a quiet lesson tucked into how we found it. Because it arrived from near the sun's direction, our practical warning time would have been short if its path had lined up exactly with Earth. From first detection to closest approach, we would have had only a handful of months to notice, to be sure, to understand. This time, the line of its travel and the line of Earth's orbit miss each other by a wide enough margin that it remains only a subject of study, not of danger. But the situation hints at how much geometry matters to our watchfulness and how important it is that we keep improving the ways we scan even the brighter parts of the sky. Set alongside that unease is a quieter sense of progress. With Oumuamua, we realized too late that we were looking at an interstellar visitor, and by the time we understood what it was already slipping away into the dark. With 2I, Borisov, we did better, following it for months and teasing out details of its chemistry and structure. And now, with 3IATLAS, we find ourselves knowing in advance, with time to prepare, to point our sharpest eyes and most sensitive instruments exactly where they need to be. All of that adds up to something rare, a once-in-a-generation chance to watch a piece of another planetary system answer our sun up close. Every spectrum, every image, every tiny change in its brightness or motion can feed into a larger picture: how other systems form their planets, what kinds of debris they throw into the dark, what survives the long drift between stars. The data we gather from this one small traveler could quietly bend our understanding of what fills the space between suns and how often worlds like ours are sprinkled through the galaxy. And even with that promise, with all the comfort of having our best telescopes ready and our equations sharpened, there is still a softer thread running underneath a simple question that sits in the back of almost every mind that hears about 3IATLAS, waiting patiently to be faced. Imagine, just for a moment, that the numbers had come out differently, that the same object we've been talking about, instead of sliding past at a safe 2.5 million miles, had its path tilted by the tiniest fraction, a whisper of a change in its approach angle, a slightly different tug from Jupiter long before we ever saw it. Suddenly, December 19th would not be the quiet passing of a distant visitor. It would be the day when an interstellar object in Earth tried to share the same place in space. To feel what that would mean, we need a sense of what 3IATLAS actually is. From its brightness and the way it sheds gas as it warms, astronomers estimate its size somewhere between 300 and 600 meters across. Settling in the middle gives roughly 450 meters, about the height of a landmark skyscraper. Not a world killer like the 10-kilometer object that ended the dinosaurs' age, but far from small on a human planet. On its own, that size would already be serious. What turns it into something far more dangerous is its speed. The asteroid that carved out the Chicxulub crater likely struck at about 20 kilometers per second. 3IATLAS is moving at around 31. In the quiet language of physics, the damage an impact does depends not just on how massive the object is, but on the square of its speed. Double the velocity, and the energy does not merely double, it grows by a factor of 4. At the velocity 3IATLAS carries, an object about 450 meters wide would hit with an energy on the order of a few thousand megatons of TNT, roughly 3,500 in many estimates. The largest nuclear device ever tested, the Tsar Bomba, released about 50 megatons. This would be many dozens of times more energetic than that single blast, concentrated into one event, in one place, within seconds. If such an object were to meet solid ground instead of sliding past us, the details of where it struck would shape what followed. Imagine, as a simple picture, that it came down over the broad middle of a continent. An instant before impact, it would still be moving faster than anything we build, compressing the air in front of it until that air itself glowed. At the moment of contact, both the object and a deep plug of rock beneath it would be vaporized, turned into a superheated mixture of gas and dust. A fireball would bloom outward, rising and expanding, hot enough to ignite anything that can burn. Close to the impact point, everything would be swept away, not just scorched, but physically scoured off the surface. Farther out, shock waves in the air would race across the landscape faster than sound, collapsing buildings, toppling trees, and shattering windows across distances measured not in neighborhoods, but in states. The ground itself would ring, carrying a jolt that instruments would record as a major earthquake, felt far beyond the horizon. The deeper reach of such an impact comes from what is thrown upward. Billions of tons of pulverized rock and dust would be lofted into the atmosphere, first as a column rising above the crater, then as a spreading veil. Within hours, that veil would begin to drift across the hemisphere, stealing a fraction of the sunlight before it can reach the ground. Temperatures would begin to slip, at first just by a few degrees, adding an extra edge to winter in places that were already cold and bringing frost to places that were not expecting it. Around the impact, fires sparked by thermal radiation would run together, filling the air with smoke and soot and thickening that dim cloak overhead. By then, the disruption would no longer be just a local disaster. Far from the crater, crops would be standing under cooler, duller light. In regions already under snow, the extra cooling would deepen and lengthen the freeze. In others, where winter is usually gentle, unexpected frosts would creep in. Meanwhile, the shock that raced through Earth's crust at the moment of impact would have stressed other fault lines, coaxing out secondary earthquakes and, in some places, undersea landslides that could send tsunamis toward distant shores. Near the site itself, the scar on the surface would be a wide, raw crater several kilometers across and a kilometer or more deep. What was a quiet landscape would become a long-lived wound on the planet. Even in a case like this, it would probably not be enough to wipe out all human life. The object that ended the dinosaurs' long age was much larger and delivered thousands of times more energy to the planet. But the blow to our civilization, the systems we rely on for food, water, power, and stability, would be profound, tilting the calm, predictable climate into something harsher. Researchers who model such events find that an object on the order of 500 meters across, striking land at typical asteroid speeds, could cause regional destruction and years of global climate disturbance. An interstellar object like 3IATLAS, arriving faster than those models usually assume, would only deepen those effects. The numbers suggest a future in which humanity might survive, scattered and struggling, but the world we recognize, the intricate web of modern life, would be permanently altered. If instead the impact point lay in the ocean, some might hope the water would soften the blow. In practice, the opposite is often true. At these speeds, the object does not gently splash down and sink. It punches through the surface, transferring its energy to the water in an instant. A vast volume of seawater would be blown outward and upward, forming a temporary cavity that would then collapse. The result would be a train of towering waves racing away from the impact site, their heights measured in tens of meters, their crests moving at highway speeds toward every nearby shore. Imagine such a strike somewhere in the open Atlantic. The waves would not care about borders. Coasts on both sides of the ocean, the eastern seaboard of the Americas, the Caribbean islands, the western shores of Europe and Africa would feel their arrival. Low-lying cities and towns that have grown up along harbors and river mouths would be especially vulnerable. Their streets and buildings never designed for walls of water pushing far inland. Beyond the immediate flooding, the atmosphere would again be changed. In addition to rock and seabed material thrown skyward, immense amounts of seawater would be vaporized and carried high into the air. Water vapor is itself a powerful greenhouse gas, and in the short term, it could drive strange, intense weather storms forming where they almost never do, rain falling in sheets where the air is usually calm. Then, as dust and soot dimmed the sun, that extra moisture would condense and fall, sometimes as heavy snow far from the impact, pushing ecosystems and food systems into deeper stress. When people who think about planetary defense lie awake at night, these are the chains of events they trace quietly in their minds, not to indulge in fear, but to understand what is at stake. They take the simple facts that 3IATLAS was discovered in October 2024 and that its closest approach comes in December 2025. And they ask what it would mean if the line of its path overlapped perfectly with Earth's, 14 months of lead time sounds generous when you say it once. Yet, when you remember how slowly we can build and launch large missions, and how carefully such missions must be planned, that span contracts quickly. NASA's DART mission, which nudged a small moonlet called Dimorphos in 2022, is often held up as a sign of hope. It showed that, given years of preparation and a relatively slow target, we can change an asteroid's path by a tiny but measurable amount. A fast-moving interstellar body of this size would demand far more energy and precision than anything we have yet attempted. Experts in the field have been frank about this. If we were to discover a large object on a true collision course with less than a year to spare, our room to maneuver would be very narrow. For familiar near-Earth asteroids, which we map and monitor over decades, we might be able to shift their paths, given enough warning. For a stranger arriving suddenly out of the glare near the sun, on a steep, high-speed trajectory, there is a real possibility that all we could do is prepare to endure the impact, rather than prevent it. In the real world, though, with 3IATLAS, that is not the story we face. The careful fits to its orbit show a clear miss by about 2.5 million miles. The lines on the astronomers' plots do not cross. They pass safely by. December 19th, 2025 will come and go with this object as a point of interest in the sky rather than a source of harm. The nightmare remains only in the realm of what if, a thought experiment we can explore from a safe distance. Yet even as we take comfort in that, the exercise leaves behind a quiet, persistent understanding. There is nothing in the laws of nature that forbids a similar object from one day having a different trajectory, one that does intersect with ours. Sooner or later, the geometry will not be so kind. The question that lingers is whether, by the time that happens, we will have given ourselves better tools, better warning, and better options. And that thought leads back, gently but firmly, to an uncomfortable realization about the way we watch the sky now, and about the gaps that still remain in our detection systems. Gaps wide enough that, even today, a city-sized object could slip through them almost unseen until it was uncomfortably close. There is a quiet truth tucked inside all of this that is hard to look at directly. With 3IATLAS, we were lucky, not because it is harmless, but because it wandered through one of the weakest points in the way we watch the sky and still let us notice it in time to study it. It slipped out of the dark along a path where our vision is thinnest, and yet we caught a glimpse that should feel less like comfort and more like a soft, persistent warning. Most of the time, when people imagine planetary defense, they picture an invisible dome of technology around Earth. A neat, reliable system, quietly catching every threat long before it comes close. The reality is humbler. Our early warning net is made of a small number of ground-based telescopes scattered around the world, carefully placed, carefully maintained, but still rooted to the same spinning, sunlit planet you and I live on. Some of the key surveys have names that sound almost friendly. The ATLAS telescopes in Hawaii and South Africa, the Catalina Sky Survey in Arizona, pans stars on Hawaiian mountaintops. Night after night, they take repeated photographs of the same patches of sky. Software then compares these images, looking for tiny dots that have shifted between one exposure and the next. It really is a cosmic game of spot the difference, played patiently in the dark. For objects already orbiting our sun, asteroids, and comets following well-behaved paths, this method works beautifully. But there is a limit baked into the setup, as simple and stubborn as daylight itself. All of these telescopes sit on Earth, and Earth orbits the Sunday. From the ground, there is always a swath of sky where the sun is either above the horizon or just below it, flooding that direction with glare. Point a sensitive camera there, and the detectors simply drown. There is a whole cone of space stretching away from us in the sun's direction, where anything approaching can remain hidden until geometry and time finally slide it into darker background sky. 3IATLAS came from almost exactly that bright, difficult direction. For weeks, it lived in that glare, moving closer while the sky in front of it was too washed out for our surveys to see. By the time its path carried it into a part of the sky dark enough to observe, it was already well inside the orbit of Mars, already, in a sense, in the yard of our planetary home. One astronomer compared the discovery to realizing that something had not been spotted walking up the street, but only once it was standing in the hallway. We did not watch it glide in gracefully from deep space. We noticed it when it was, in cosmic terms, already near our doorstep. It is tempting to say, well, the system still worked. We saw it. And, in a narrow sense, that's true. But there is another story, from a few years earlier, that hints at how close our luck can come. On July 25, 2019, an asteroid, later labeled 2019, OK, passed by Earth at a distance of about 72,000 kilometers, roughly 1/5 the distance to the Moon. On the scale of space, that is a near brush, and it was only recognized as it was arriving, with roughly a day of warning. 2019. OK is thought to have been around 100 meters across, large enough that, if it had struck, it could have caused regional damage and a truly terrible day for any nearby city. Its late discovery had the same root cause as our delay with 3IATLAS. It approached from near the sun's direction, out of a bright patch of sky where our nighttime surveys are almost blind. It was also moving quickly across that small observable window, making it hard for automated systems to lock on and track it before it slipped away again. By the time astronomers fully understood what had just happened, the asteroid was already past us and receding, a potential disaster glimpsed only in hindsight. Stories like that sit alongside another uncomfortable number. Based on careful statistical studies, NASA estimates that there are on the order of tens of thousands of near-Earth asteroids, larger than about 140 meters, big enough to cause serious regional harm if they hit the wrong place. We have found only a fraction of them. Many thousands more are still out there, quietly circling the sun on elongated paths that sometimes cross Earth's orbit and sometimes miss us by wider margins. We suspect they exist because of how the population behaves as a whole, but we do not yet know their individual names or tracks. And those are just the local objects, the ones bound to our star and moving in ways we can eventually predict. Interstellar visitors, like 3IATLAS, are different in a deeper way. They do not belong to the Sunday. They arrive from random directions, at higher speeds, on one-time paths we cannot forecast ahead of discovery. Until one wanders close enough that sunlight reflects from it into our telescopes, it is effectively invisible. In the best case, we might see such an object months before its nearest approach. In less kind geometry, we might notice it only weeks or days before it sweeps past. It is natural to ask, in the hush that follows those realizations, can we do better? The most straightforward answer that astronomers give is simple in principle, even if it is demanding in practice. To close the blind spots created by the sun's glare and Earth's day-night cycle, we need to put more of our eyes into space itself. A telescope floating far from Earth, looking in infrared light that can pick out the gentle warmth of dark rocks against the colder background, would not be limited by weather, sunrise, or sunset. From the right vantage point, It could peer into the very regions of space that are hardest for us to monitor from the ground. One such mission, called NEO Surveyor, is being built with exactly this purpose in mind. Rather than taking pretty pictures, it is designed as a patient hunter of heat, tuned to spot the faint glow of near-Earth asteroids hundreds of meters wide. Placed at a gravitationally stable point between Earth and the Sun, it will have a clear view of the sunward side of our orbit, the very zone that trips up our ground-based searches. Simulations suggest that, over about a decade of operation, it could find the vast majority of potentially hazardous asteroids above a certain size. The idea is elegant. The path to getting it into space has been less so. Building, testing, and launching such a mission costs money and time, and planetary defense, for all its quiet importance, does not always sit at the top of political priority lists. Budgets tighten, schedules slip, and a telescope meant to watch for rare but consequential dangers ends up waiting behind more immediate concerns. On paper, the price of NEO Surveyor is large. Compared to what our species spends on many other single pieces of hardware, it begins to look small, a kind of cosmic insurance policy that is easy to overlook, precisely because its success would mean nothing dramatic ever happens. Even imagining a perfect network of telescopes, both on the ground and in space, there is another constraint that does not go away: time. Finding a new moving dot in the sky is only the first step. To know whether that dot poses any real danger, astronomers need to follow it over days and weeks, measuring its position again and again. Each new measurement tightens the fit to its orbit, shrinking the cloud of possible future paths. At first, that cloud can be huge, including both safe misses and sometimes a small chance of impact. As more data comes in, the cloud usually narrows and slides away from Earth. This is why, when a new near-Earth object is announced, you sometimes hear that there is a tiny probability of collision on some date, decades in the future, and then, quietly, that probability drops to zero after more observations. The early uncertainty is not a flaw. It is just the geometry of trying to predict a future from a handful of points. But it also means that, if we discover something dangerous with only a little time to spare, we will spend precious days just making sure our understanding is correct before anyone can act. With 3IATLAS, the timeline is generous by those standards. Roughly 14 months separate its first detection from its closest pass. That span allows for careful tracking, rechecking, and deep study. By contrast, 2019 OK gave us only a day between clear recognition and its flyby. And in the darker thought experiment, where an interstellar object comes straight at us from the sun's direction, and we see it only a week before impact, the space for meaningful action shrinks almost to nothing. In that scenario, there would be no time to design and launch a mission to push it aside. Large rockets are not things we can improvise in days. They require years of planning, long manufacturing chains, coordination, and careful checks. With a week's notice, all we could realistically do would be to use our knowledge to warn, to estimate an impact zone as best we could, and to move people out of the way where that is possible. The focus would shift from prevention to protection, from changing the sky to softening the blow on the ground. This is the context in which offices with quiet names do their work. Inside NASA, the Planetary Defense Coordination Office exists for exactly these questions. Its task is to keep track of potentially hazardous objects, help improve our ability to find them early, and plan how we might respond if one day the calculations show that something truly large is on course to meet us. Give such a team 5 or 10 years warning, and they can explore options for deflection, Give them 5 months, and the menu of possibilities shrinks. Give them 5 weeks, and they are no longer talking about moving the object, only about preparing the world beneath it. Layered over all of this is a more human complication: attention. Because our measurements start with uncertainty, there are times when an object briefly appears on risk lists, only to be removed later. News stories flare, asteroid might hit Earth, and then fade when better data arrives. Over time, that cycle can wear down the sense of urgency in the wider public. The danger is that when a real, well-confirmed threat does appear one day, a warning might sound like just another passing headline. To help sort signal from noise, scientists use tools like NASA's Sentry system, which constantly checks known near-Earth objects for possible future impacts, and the Torino scale, which ranks potential threats on a simple scale from 0 to 10. Most new objects stay firmly at the quiet end of that scale. A rare few climb higher before dropping back down as more data refines their paths. But all of these tools share a quiet, fragile dependency. They only work on objects we have actually seen. If something approaches through a blind spot and slips by without ever crossing a detector's field of view, the cleverest software in the world will have nothing to analyze. So we come back, gently, to 3IATLAS. We found it. We measured it. We know that it will not strike Earth. Its path and ours miss by a comfortable margin in human terms. On December 19th, it will simply pass through our neighborhood, a silent traveler from another star system, illuminated for a short while by our Sunday. But the manner of its arrival, that it could slide inside Mars's orbit before we noticed, whispers something important. The gaps in our watch are not abstract. They are real places in the sky where big things can hide. Somewhere in the long future, or perhaps closer than we like to imagine, another object will come through one of those gaps on a much less gentle trajectory. Thinking about 3IATLAS gives us a chance to listen to that warning without panic, to feel the mix of beauty and vulnerability in the way we sit here on a small blue world, learning, slowly, how to see a little farther into the dark. Even if we someday manage to stitch up all the holes in our watchful net around Earth, another question waits quietly just beyond it. Suppose, for once, everything worked in our favor. We spot a dangerous object early. Its path is clear, the calculations are solid, and there is no doubt, in 5 years' time, it will cross the same place in space that our planet occupies. Not a near miss, but a meeting. What then? Would 5 long years be enough to change that outcome? Or would they simply give us more time to live under a slowly growing shadow? It's here that stories on screens have given us a strangely comforting illusion. Many of us carry movie scenes in the back of our minds. Brave crews landing on tumbling rocks, drills biting into alien stone, heroic sacrifices, and last-minute explosions that shatter a threat into harmless glitter. Those images are exciting and tidy. They leave us with the sense that if anything truly awful were coming, someone somewhere would strap into a rocket, fly out, and fix it. The real tools we have are quieter, smaller, and far more limited than that. There is, however, a sliver of good news to hold on to. We are not completely helpless. On a calm night in September 2022, a small spacecraft called DART, short for Double Asteroid Redirection Test, ended its journey by throwing itself into a tiny moonlet named Dimorphos. It was not a dramatic, human-piloted mission, just a box of electronics and metal, guided by careful software and decades of planning. Traveling at several kilometers per second, It met the asteroid and vanished in a brief, bright puff from Earth. Telescopes watched as material burst away from the impact site, forming a tail of dust that stretched into space. In the weeks that followed, astronomers measured Dimorphos's path around its larger companion, Didymos, with intense care. Before the collision, the little moonlet took a certain number of hours to complete each orbit. Afterward, that time had changed by more than half an hour. A tiny nudge, delivered at the right moment, had shifted its motion. For the first time, we had proof that we could deliberately move a natural object in space, even if only by a small amount. It was a beautiful result, and many people who had worked on the mission described it as a first step toward learning how to protect our world, and they were right to be proud. But there are details that the gentle glow of headlines didn't always linger on. Dimorphos was, in many ways, a dream target. It was only a few million miles from Earth, slow enough, on a stable and well-studied orbit, and there was no danger at all in missing our mark. If the attempt had failed completely, nothing on Earth would have been harmed. The experiment was about understanding and practice, not about saving ourselves. When we turn our thoughts back to something like 3IATLAS, the picture changes. Could we repeat a DART-style maneuver on an interstellar object if we needed to? The honest, quiet answer, for now, is probably not. The reason lies in a simple idea from physics called momentum, the product of an object's mass and its speed. When DART hit Dimorphos, it transferred its own small momentum into the asteroid, causing a subtle change in the asteroid's velocity. But that change was measured in millimeters per second, a tiny tweak, just enough to add up over months and years into a meaningful shift in position. That works well if your target is relatively small, already loosely bound to a safe path, and you have a lot of time. It is like nudging a train by shifting the track slightly when the train is still far from the station. By the time it arrives, that little change has placed it on a different platform entirely. For an object like 3IATLAS, things are much more demanding. It is likely several times larger in diameter than Dimorphos, which means far more mass, and it is racing through space at about 31 kilometers per second, much faster than the asteroid DART met. The faster and heavier something is, the harder it is to steer. If we discovered that such an object were going to hit Earth in a year or two, we would need to change its speed by meters per second, not millimeters, to make it miss us. That is a difference of thousands in the required momentum change. One small impactor would not be enough. We would need something much more massive, or a whole fleet of impactors, or both, and each of those options would take years of design and launch campaigns we do not yet have sitting ready on the shelf. This is where a more sobering idea enters the room: using nuclear devices, not as movie props that blow an asteroid into dramatic shards, but as tools to push. The image from fiction of drilling into a rock and setting off an explosion inside it would be a terrible plan in reality, more likely to turn one hazard into a cloud of smaller, still dangerous fragments. The approach that serious studies consider is gentler and more precise. You do not place the device on the surface, you detonate it nearby. In that kind of standoff explosion, most of the energy races out into space, but a portion washes over the asteroid's surface, vaporizing a thin layer of material. That sudden burst of gas and plasma jets away from the object, and, like exhaust from a rocket engine, it pushes back. For every bit of material thrown outward, there is an equal and opposite nudge on the asteroid itself. The hope is to lean on that recoil just enough to slightly change the object's path years before it reaches Earth. This concept called nuclear deflection, has been examined in detail in technical reports and quiet workshops. For very large, solid asteroids with limited warning time, it often comes out as the most powerful option we can realistically imagine using. A single device of a few megatons, timed and placed correctly, could, in theory, provide a meaningful shove. But all of that rests on a tower of assumptions and delicate requirements. The explosion must occur at just the right distance. Too close, and you risk cracking the object apart, letting gravity or motion pull the pieces along nearly the same path. Too far, and the energy fades to heat and light without doing much work. The response also depends heavily on the asteroid's nature. A compact, rocky body would transmit the push differently than a loose clump of boulders barely held together by their own gravity. To plan such a mission properly, you would need to know the object's composition, its internal structure, how fast it spins, and how its surface responds to heat. All details that take time and careful observation to pin down. Then there is the layer of human law and trust. For decades, nations have agreed not to place nuclear weapons in space. That agreement, written into treaties after years of tension, is one of the reasons our skies remain as peaceful as they are. In an extraordinary emergency, countries might be willing to make an exception, but that would require a level of international cooperation that is hard to imagine even in calm times. Asking rivals to share technology, plans, and launch windows while a potentially world-ending object is on its way would be as much a political challenge as a technical one. Even if we set aside all those difficulties and imagine that a deflection mission is approved, built, and launched, interstellar objects add another twist. Unlike near-Earth asteroids, which we can study over many orbits, a visitor from another star gives us only one brief chance to learn what it is made of. Is it a roughly solid chunk, a fragile pile of icy rubble, a comet-like body with thick, volatile layers? Each possibility changes how it would react to a blast or a series of impacts. If the structure is loose, like a heap of gravel, any forceful push might simply rearrange the pieces, sending them along nearly the same overall path. The large threat could become many smaller ones, still arriving together. If the object is rich in ices, the heat from a nuclear device might trigger intense outgassing, turning the body into an unpredictable engine as jets of vapor thrust in directions we did not fully anticipate. Instead of guiding it neatly away, we might simply trade one uncertain trajectory for another. And always, the clock is ticking. DART took close to a decade to go from an idea on paper to a real spacecraft hitting its target. That long span included design work, construction, testing, launching, and cruising to the asteroid system we had chosen years in advance. In the thought experiment with 3IATLAS, we speak of 14 months between discovery and closest approach. With our present pace and infrastructure, there is simply no way to design, approve, build, and launch a complex deflection mission in that kind of time, especially when the target is new to us. Other proposals for moving asteroids sound wonderfully gentle. One is the gravity tractor, in which a spacecraft simply hovers near a threatening object for years, letting its tiny gravitational pull tug imperceptibly on the asteroid's motion. Over long stretches of time, that almost invisible pull could add up to a helpful shift. Another idea is to use powerful lasers to slowly vaporize material from one side of an asteroid, creating a continuous, controlled jet of escaping gas that acts like a small thruster. Engineers have even imagined sending not just one impactor, but a whole flotilla of them, each adding its own little push, All of these methods share a common requirement: patience. They work best when you have decades of warning and a target moving slowly enough and predictably enough that small forces can reshape its future. They are tools for a careful gardener, not for someone trying to jump out of the way of a car that has suddenly appeared at the edge of the crosswalk. That may be the most important quiet truth of planetary defense. It is less like a dramatic last-minute rescue and more like insurance. The only way it can truly protect us is if we build it long before we know we need it, by mapping most of the large near-Earth asteroids, by testing methods like DART, again on different kinds of targets, by putting new eyes in space to find the ones still hiding. Those are investments in a future problem that might not arrive for generations, which makes them easy to postpone and easy to forget. Interstellar objects, in that picture, are like cars that do not follow the usual traffic patterns at all. Most of the time, the bodies that cross Earth's orbit do so on familiar, charted paths we can learn and anticipate. A visitor from another system, by contrast, can come in fast and steep from an unexpected direction, like a vehicle racing through a red light from the corner of your eye. By the time you notice, the margin for action is already thin. After the DART impact, one of the scientists involved said something simple and modest. "We have shown that we can move a small asteroid a little bit." It was a gentle reminder not to mistake a first success for a complete solution. The experiment proved that nudging a rock in space is possible. It did not prove that we can always do it in time or at the scale needed to handle every kind of threat. So we stand, for now, in an in-between place. We know more than we did a decade ago. We have tested one method and are dreaming up others. We can picture ways to push a dangerous object aside, at least in principle, if we are given enough warning and the right kind of target. But against something like 3IATLAS on a true collision course, with only a short span of time to prepare, our tools would be small, our choices limited, and our hopes pinned far more on early sight than on last-minute heroics. Even if we somehow knew, long in advance, that an object like 3IATLAS was truly on its way toward us, the kind of help we could offer ourselves might look very different from the heroic images people sometimes carry in their heads. With 14 months of warning and no real way to push something that fast and that massive aside, most of what we could do would not involve rockets at all. It would begin with watching, measuring, and trying to understand the visitor as clearly as we possibly can. That may sound small compared to the idea of saving the world, but in this kind of situation, knowledge is one of the few tools that actually scales. The better we understand what an object is made of, how it holds together, how it spins and sheds material, the more honestly we can predict what it will do. That matters whether we are hoping for a last, small chance to deflect it or preparing ourselves to endure whatever comes. And right now, even with 3IATLAS on a harmless path, the way it behaves is strange enough to unsettle people who have spent their lives studying comets. When astronomers aim their instruments at this dim smudge of light, they are not just trying to capture a pretty image. They use a technique called spectroscopy, which is really just a careful way of spreading the light out into a rainbow and looking for dark and bright lines within it. Different molecules absorb and emit light at very specific colors, so that rainbow becomes a quiet barcode, a chemical fingerprint traced across space. From that pattern, they can tell which gases are billowing off the object as the sun warms it. In 3IATLAS's spectrum, they see familiar signatures: water vapor, carbon dioxide, carbon monoxide. These are the old friends of comet science, the same ingredients that turn many icy bodies in our own system into glowing, tailed wanderers when they fall inward toward the Sunday. In that sense, 3IATLAS looks reassuringly comet-like. It is not made of exotic metal or some unknown element. It is, at least on the surface, a kind of dirty snowball, much like the ones we know. But the more closely they look, the less neatly things line up. The ratios between these gases are off compared to the comets we have cataloged around our own star. The balance feels wrong, as if the recipe came from a different kitchen entirely. That idea is not new. Our second known interstellar comet, 2I, Borisov, already showed that visitors from other systems can be chemically odd. Its carbon monoxide content was many times higher than is usual here, a sign that it may have formed in a colder, more distant region around its home star. 3IATLAS seems to be continuing that theme of difference, but with its own peculiar twist. One of the strangest things is how its outgassing and its brightness refuse to march in lockstep. For a normal comet, when sunlight warms the surface and ices sublimate, the gas and dust released form a coma, a hazy envelope, and the whole object grows brighter in a fairly predictable way. With 3IATLAS, the light curves astronomers plot over time are jumpier, less orderly. The way its shine waxes and wanes suggests that its surface is patchy, with some regions bright and icy, others darker and more crusted over. As it spins, different faces turn toward the sun, waking up and then cooling off again. From the rhythm of its brightness, scientists estimate that it completes a full rotation somewhere in the range of 8 to 12 hours. That is a quick spin for something hundreds of meters across. If the body were just a loose heap of rocks and ice, what they call a rubble pile, centrifugal forces at that spin rate might be enough to tear it apart. The fact that it remains intact hints at some internal strength, some kind of cohesion binding it together more firmly than a simple pile. Those hints bring back old questions from another visitor. Oumuamua, the first interstellar object we recognized. Its non-gravitational acceleration, that tiny, persistent extra push that gravity alone could not explain, sparked a flurry of ideas. Perhaps hydrogen or other very light gases were streaming off its surface in ways our instruments could not see. Perhaps its shape and tumbling motion created an uneven rocket effect from subtle outgassing. And yes, some even wondered if it might be a piece of technology, a thin sail driven by starlight. Most scientists leaned hard toward natural explanations and still do. Yet the truth is that none of those explanations has fully closed the book. A faint thread of mystery remains. Now, watching 3IATLAS pick up about 15% more acceleration than visible outgassing alone can explain, that thread tugs again. One family of ideas that has grown in recent years involves so-called supervolatiles, substances that can turn from solid to gas at very low temperatures, far out in the cold. While water and carbon dioxide need a certain level of warmth to wake up, ices made of things like molecular nitrogen can start drifting away much farther from the sun, leaving little or no obvious signature. You might not see dramatic jets or a bright, thick coma, but you would still feel the cumulative push of that invisible exhaust in the object's motion. Some researchers have suggested that Oumuamua might have been largely made of such exotic ices, perhaps something like a chip off the surface of a nitrogen-rich world. If that were true, quiet sublimation could have given it a gentle shove without the usual cometary display. Similar thoughts are now circling 3IATLAS. Maybe we are only seeing the tip of its activity. the part that happens to involve more familiar gases. The rest could be hidden, both from our cameras and our more comfortable theories. Then, there is the matter of time. 3IATLAS has likely been traveling between stars for an unimaginably long period. Millions, perhaps tens of millions of years. Interstellar space is thin, but it is not empty. High-energy particles called cosmic rays stream through it constantly, striking whatever happens to drift in their path. Over spans that long, those impacts can change the chemistry of the outer layers of an object, turning simple ices into more complex organic films, rearranging the lattice of crystals in rock, darkening and hardening the very skin that faces the void. This slow transformation is sometimes called cosmic weathering. Some scientists think Oumuamua may have carried a thick, carbon-rich crust born of that constant radiation, a shell that behaved almost like a protective armor. If 3IATLAS has grown something similar during its lonely journey, that might help explain why its surface seems so uneven, why some regions respond to sunlight in ways that confuse our models built on fresher, less altered comets. All of these threads, odd gas ratios, patchy brightness, unexplained acceleration, ancient weathering, are being pieced together from a distance that feels almost absurd. We are, after all, trying to read the history and structure of a tumbling, icy rock from millions of miles away, using only the light that bounces off it and the slight wobble in its path. Even our sharpest tools, like the James Webb Space Telescope, reach their limits. They can tell us about the overall glow, about the average composition of the gases streaming away, about broad changes in time, but not about small cliffs, cracks, or jets. It is a bit like trying to understand a distant mountain by watching its reflection ripple on the surface of a lake. Patterns emerge, and you can learn a great deal with patience and careful math, but some details will always stay blurred. We will never send a probe to land on 3IATLAS. We will never bring a piece of it back to a lab. By the time we fully digest the measurements we are making now, it will already be on its way back into the deep dark, receding forever. Still, there is one more question that pulls the mind back from all that abstraction to something more intimate. Before it was thrown out, where in its original home did this object come from? Our own solar system offers a kind of map: rocky, metal-rich bodies near the sun, icy giants, and frozen worlds far beyond, belts of debris marking different temperature zones in our past. If 3IATLAS formed in the cold outskirts of another system, its version of our Kuiper belt, it would naturally carry more ices, more supervolatiles, more of the ingredients we are now glimpsing in its spectrum. If it was born closer in, it might be denser, more rock than ice, its surface only later frosted as it wandered outward. The chemistry and the way it behaves under sunlight lean toward the colder origin story. It feels, in that sense, like a messenger from the far edges of someone else's planetary nursery. Flung away during some early chaos, large worlds migrating inward and outward, gravity tossing small bodies around like pebbles in a storm. After that single, violent eviction, it simply drifted, its path straightening into a long, deep arc through the galaxy, until our sun's pull finally turned its head for this one close pass. All of this, the physics, the chemistry, the long journey feeds into a more human curiosity that keeps finding its way to the front of people's thoughts. When the date we have circled finally arrives, when 3IATLAS makes its nearest approach and slides past our planet's orbit, what will that actually look like from here? Will it be a bright, obvious visitor hanging in the sky, or only a faint smudge only cameras can love. And in those short, precious hours around closest approach, what exactly will the world's observatories be doing, pointed and listening, while this traveler whispers by? Sooner than it feels, the quiet theories will have to meet the reality of that night. And to understand that part of the story, we have to turn gently from what 3IATLAS is to what December 19th itself will be like for the people watching under its path, and for the scientists waiting on the other side of their telescopes. From here on, the questions become more everyday, not about impact energies or orbital elements, but about something simpler. On that night, if you step outside and look up, will you actually see this traveler with your own eyes? For most people, the honest answer is probably not. Interstellar or not, 3IATLAS still has to obey the same rules of light as everything else. Astronomers can already estimate how bright it will appear at closest approach, using its distance, its size, and how much sunlight its dusty coma will reflect. Those estimates put it at a visual magnitude of around 10 to 12. On the odd little scale that astronomers use, smaller numbers mean brighter objects. The very faintest stars a healthy human eye can pick out under a perfectly dark, rural sky sit around magnitude 6. Planets like Venus and Jupiter are far brighter still. A magnitude of 10 or 12 falls well below that naked eye threshold. That does not mean the sky will be entirely silent. It just means that, without help, 3IATLAS will be hiding in that quiet realm where only glass and mirrors can reach. To have a chance of seeing it directly, you would need a modest telescope, something with a mirror or lens a few inches across, a steady mount, and a sky not drowned in city glow. You would find the right patch of stars from a chart, focus carefully, and then look for a small, soft point or smudge that is not quite where it was a few minutes before. That motion is part of the strange magic of watching a near visitor. Stars remain, for us, fixed. Their shifts are so slow that generations pass before any pattern changes. Planets wander a little from night to night, but an object passing only a few million miles away moves fast enough that even over the length of a single observing session, you can see it slide gently against the starry background. Through the eyepiece, 3IATLAS would not streak dramatically like a meteor. Instead, it would creep, star by star, like a distant aircraft crossing a field of lights, except that this aircraft is a half-kilometer of ice and rock from another star system, climbing through our neighborhood at tens of thousands of miles per hour. Where you are on Earth will matter. During its closest approach, the geometry of its path favors the southern half of the planet. Places like Chile, South Africa, Australia, and New Zealand will have the best view, with the object rising higher above the horizon and spending longer in dark skies. Observers farther north will still have chances, but 3IATLAS will cling closer to the horizon, its light softened and blurred by extra layers of atmosphere. Professional observatories in Hawaii and the Canary Islands will be able to follow it, but the most generous window truly belongs to skies below the equator. Even if you never touch a telescope yourself, the night will not be closed to you. Many of the people who do have those instruments will be sharing what they see. Space agencies and observatories have already set aside time to point large telescopes at 3IATLAS and stream the results. Cameras far more sensitive than the human eye will gather photons from the object and turn them into images you can watch on a screen. A small, moving blur, sometimes with a faint tail, slipping across a fixed grid of stars. On mountaintops, giant mirrors will be quietly doing their work, The European Southern Observatory's very large telescope in Chile, with its 4 great eyes, will follow the visitor across the southern sky. The Gemini and Subaru telescopes, perched high on Mauna Kea in Hawaii, will take their own turns, catching it as geometry allows. These instruments can see things thousands of times fainter than the dimmest star your eyes can manage, and they will be feeding their data continuously into the hands and minds of scientists around the world. But the most revealing views will come at wavelengths we were not born to see. Out beyond Earth's atmosphere, the James Webb Space Telescope will look at 3IATLAS in infrared light, the soft glow of heat that every object above absolute zero gives off. In that glow are temperature maps, tiny differences that tell you which regions are covered in fresh, reflective ice and which are darker, more crusted, or more active. Jets of gas and dust, invisible light, may stand out clearly as warmer or cooler patches. Webb's instruments will turn those subtle patterns into clues about structure and composition that no human eye, no matter how keen, could ever gather alone. Hubble, older but still sharp, will join in from its own orbit. It can watch in visible and ultraviolet light, where certain gases leave bright fingerprints when they are broken apart by sunlight. Water molecules, for instance, can fluoresce in ultraviolet as they are split and scattered. By mapping that glow, Hubble can help show which parts of the coma are most active, where the outgassing is strongest, and how it changes as the object rotates. Between them, Webb and Hubble will be listening to different voices in the same small song. What many people never see is how precious those listening hours are. Time on these major telescopes is not simply reserved because something sounds interesting. It is fought for. Months before 3IATLAS's closest pass, astronomers around the world wrote detailed proposals explaining exactly what they hoped to measure, why it mattered, and what instruments they needed. Committees read and rank those requests, trying to decide which projects could make the best use of limited nights and limited orbits. The fact that this one object has earned slots on multiple flagship observatories tells you how special the scientific community considers this moment. For them, it has the feel of a once-in-a-generation event, the kind of passage that will be written about and revisited for years. The questions they hope to answer are both simple and deep. One goal is to pin down the size and shape of 3IATLAS with far more precision than we have now. At the moment, our estimates of its diameter span hundreds of meters. High-resolution images taken near closest approach, when it is brightest and nearest, can narrow that down, revealing whether it is rounded, elongated, lumpy, or perhaps even accompanied by a tiny companion. Its spin rate, how quickly it rotates, will be refined from the subtle flickers in brightness as different faces turn toward us and toward the Sunday. Another priority is to catalog as completely as possible the gases and dust it exhales as it warms. Every molecule identified is a small piece of a puzzle, a hint about the temperature and chemistry in the part of its birth system where it formed. Some of those molecules will be familiar organics, carbon-bearing compounds that, in other places and times, can serve as the raw ingredients for life. Their presence here would not mean that anything living ever clung to this object. Simple organic chemistry is common in cold interstellar clouds and on icy grains, but comparing their abundance and variety to what we see in our own comets can tell us how similar or how different the cosmic pantry is from one star to another. One astrochemist once described interstellar visitors as sample return missions we didn't have to launch. It is a gentle way of saying that each of these objects is a little piece of another world delivered to us for free. When we spend years and vast sums to collect a few grams of dust from an asteroid in our own solar system, we do it because those few grams can answer questions about how planets form and change. An object like 3IATLAS brings with it the frozen record of a completely different disk of gas and dust around a completely different sun. We cannot scoop any of it into a container, but we can read what evaporates in the warmth of our star and infer the rest. You do not need a giant observatory to help with that reading. All across the world, amateur astronomers are preparing in their own quiet ways. People with mid-sized telescopes and sensitive cameras, often set up in backyards or small domes, can take repeated images that track how the object's brightness rises and falls over time. Organizations that coordinate citizen science will gather those images and measurements, stitching them together into continuous light curves that fill in the gaps between big observatories' scheduled windows. This matters because no single telescope, however powerful, can watch 3IATLAS constantly. Hubble must divide its time among many targets. Ground-based giants can be clouded out or forced to pause as the object sets below the horizon. While one site sleeps, another part of the Earth turns into view. An amateur observer in Australia might pick up the thread where a professional one in Chile had to let go and then hand it off again to someone in South Africa. In that way, a loose, global network of eyes can keep the story going, frame by frame. There are even more subtle measurements planned. As 3IATLAS passes by at its closest point, still far beyond the moon, but near enough in cosmic terms, Earth's gravity will tug on it ever so slightly, bending its path by a small amount. By tracking that bend with exquisite care, scientists can back out an estimate of the object's mass. Combined with its measured size, that mass gives an average density, a number that hints at how porous or solid it is, whether it is more like a snowbank, a pile of gravel, or a chunk of stone wrapped in ice. Radar, too, will have its moment, if the timing and distance cooperate. Facilities like the Goldstone Deep Space Communications Complex can send out beams of radio waves and listen for the echo off the visitor's surface. The delay between transmission and return reveals distance down to a precision that optical methods cannot match. The way the echo is spread and smeared tells of surface roughness and spin, smooth ice, fractured rock, and loosely packed dust. Clouds all scatter radio waves differently. The window for such experiments will be short, perhaps only hours, when geometry, distance, and equipment all line up, but in that narrow slice of time, a great deal can be learned. And then, as all things do, the moment will pass. 3IATLAS will slide on, out of the inner solar system, and back toward the long, cold reaches between stars. The images will dim, the signal in the data will grow faint. Telescopes will turn back to galaxies, nebulae, and the slower, more predictable rhythms of planets and stars. What remains will be the traces, terabytes of recorded light, spectra, timing measurements, radar echoes, all stored away on servers and in notebooks. From that quiet archive, students and scientists will draw for years. Doctoral theses will be written about its chemistry, its spin, its structure, its odd acceleration. New models of planet formation, of interstellar weathering, of comet physics will be tested against what this one object chose to show us as it passed. In the end, the most lasting part of December 19th may not be what anyone sees with their eyes, but the way this small, fast traveler enlarges our understanding of how worlds are made, how they are thrown away, and what waits for them in the dark between suns. Answers we cannot get in quite the same way from anything that chose to stay bound to our own star. From the ground, all of this can feel abstract until you remember what will actually be happening on that December night. Somewhere high above the clouds, far beyond the reach of any airplane, a small, ancient traveler from another star will be sliding past our world. It does not know we are here. It does not care. It began its journey in a place we will never visit, around a sun we will never see with our own eyes, and yet, for a brief moment, its path and ours nearly touch. People scattered across Earth will be following a moving dot on screens or through telescopes, all sharing the same quiet thought. Something truly foreign is passing through our neighborhood. Moments like that tug gently at our sense of scale. They remind us how tiny our blue planet is, how local our usual worries are, and how much of the universe lies outside our notice. If one interstellar object, like 3IATLAS, can wander close enough for us to measure it, almost by chance, it raises a softer, unnerving question. How many others are out there, drifting through our solar system right now, unseen? The uncomfortable answer is that 3IATLAS is almost certainly not alone. It is just one member of a much larger, mostly invisible crowd. In the last few years, we have officially recognized 3 interstellar visitors: Oumuamua in 2017, 2I Borisov in 2019, and now 3IATLAS, 3 in a short span of time. After centuries of watching the sky, that sounds small until you remember how narrow our window really is. We only notice the objects that happen to be big enough, bright enough, slow enough, and lucky enough to pass through the tiny volume of space we are actually surveying at any given moment. It is a little like standing in a forest at night with a small flashlight, seeing 3 animals in the beam, and then trying to guess how many more are moving just beyond the circle of light. Your glimpse tells you the woods are alive, not empty, but it does not tell you everything that is there. When astronomers take the few interstellar objects we have seen and work backward with statistics, they end up with numbers that are both fascinating and faintly chilling. Some studies suggest that at any given time, there may be on the order of hundreds of interstellar bodies within the orbit of Neptune, little lumps of ice and rock passing through silently, never coming close enough or shining bright enough for our current surveys to pick them out. If that is true, then the 3 we have identified so far are just the tiniest tip of a much larger population. The detection rate hints that we are only seeing a fraction of 1% of what is actually there. Most of those unseen visitors are probably small, measured in meters rather than hundreds of meters. At those sizes, they are all but invisible unless they pass very close to Earth or flare in some unexpected way. Models suggest that objects 100 meters across or larger may sweep through the inner solar system several times a year. Our telescopes, limited by sensitivity, blind spots, and the sheer size of the sky, miss almost all of them. They arrive, curve around the sun, and leave again without ever earning a label. And yet, not every interstellar wanderer simply glides through and escapes. There is a quieter possibility that some of them have been caught. Under just the right circumstances, if an object passes near a giant planet like Jupiter or Saturn, gravity can reach out and steal some of its speed, turning a one-time flyby into a bound orbit. The path that was once open and hyperbolic can close into a loop. The newcomer becomes part of the sun's family, indistinguishable at first glance from the asteroids and comets that were born here. Astronomers have found a few objects whose orbits look odd enough to raise this suspicion. One of them travels around the Sun near Jupiter's distance, but does so in the wrong direction, looping backward compared to the planets. Its path is so tilted and twisted that it is hard to explain as something that formed in the same quiet, spinning disk of material that gave us the familiar planets. Some researchers have suggested that it may be an immigrant from another system, captured long ago and quietly circling ever since. If one such body exists, there could easily be others, dozens, perhaps hundreds of interstellar refugees hiding in the vast catalog of asteroids we have already logged, waiting for someone to notice how their motions give away a different origin story. When you pull back even farther, out beyond our little system, to the scale of the galaxy, that idea of refugees becomes almost inevitable. The Milky Way holds well over 100 billion stars, and we now know that most of them are attended by planets. Young planetary systems are messy places. As new worlds form and giant planets migrate inward and outward, their gravity throws countless smaller bodies around like pebbles in a stirred pond. Many of those bodies end up in distant reservoirs, like our Kuiper Belt or Oort cloud. Many others are kicked all the way out, their ties to their home stars broken forever. Simulations of those early times suggest that our own solar system must have flung billions upon billions of icy and rocky fragments into interstellar space. If that is true here, it is almost certainly true elsewhere. Multiply that by 100 billion systems, and you arrive at a staggering picture. A galaxy threaded not just with stars and gas, but with an ocean of solid debris, comet nuclei, asteroidal shards, perhaps even full-fledged planets drifting between suns. Among that debris, some pieces will be small, the size of boulders or houses. Others will be larger, cold worlds with their own internal heat, cut loose from any orbit at all. Astronomers call these rogue planets, and there are hints from the way their gravity briefly magnifies background stars that they may be more common than we once thought. Some studies even suggest there could be as many rogue planets as there are stars, or more, lonely worlds wandering the dark, perhaps with frozen surfaces, subsurface oceans, thin atmospheres, lit only by starlight from afar and the faint warmth of their own interiors. The chance of one of these big, heavy drifters blundering straight through the inner part of our solar system is extraordinarily small. Space is too wide, distances too great, and the paths of most wanderers carry them harmlessly through emptier regions. But extraordinarily small is not the same as zero, and thinking about such a passage can make the quieter, more likely dangers feel very immediate by contrast. A Jupiter-sized visitor passing near the inner planets could twist orbits, reshuffling the architecture of our system in ways life would not survive. The good news is that, on human timescales, such encounters are close enough to impossible that they live mostly in thought experiments. Smaller objects, though the ones the size of hills or city blocks, are a different story. Those are common enough across cosmic distances that we know some must be flying through our neighborhood from time to time. Every day, Earth sweeps up tiny bits of dust and rock. We see them as meteors, brief streaks of light that burn up long before they reach the ground. A few reach the surface as meteorites, carrying with them little clues about their origins. Most are clearly from our own solar system, but buried somewhere in that endless drizzle, there are almost certainly fragments that began their journey around another sun, arriving here too small and too fast for us to recognize them as anything special before they flash and vanish. Once in a while, though, the numbers stand out. In 2014, instruments recorded a small fireball over the ocean near Papua New Guinea. What caught researchers' attention later was not its brightness, but its speed, around 60 kilometers per second as it hit our atmosphere. That is faster than most bound objects should be moving at Earth's distance from the Sunday. A handful of scientists argued that this might have been an interstellar meteor, a tiny cousin to the larger visitors we have since found. The data were noisy, the conclusion debated, but the mere possibility was enough to open a new question. How many such interstellar pebbles have we already watched burn without realizing what they were? Even the directions our visitors come from may carry stories. If interstellar objects arrived only from completely random angles, their statistics would tell us one thing. But it is possible that the Sun, as it orbits the center of the galaxy, sometimes passes through regions richer in debris, remnants of old star clusters, shells of material blown out by chains of supernovae, subtle structures in the galactic disk that we are only beginning to trace. Driving along a quiet highway, you might pass mostly through clear air, and then, suddenly, your windshield splatters with insects as you cut through an unseen swarm. On much grander scales, our solar system could be moving through similar clouds of solid matter, some of which finds its way into the inner system. All of this drifts back, gently, to the limit that keeps appearing in our story. We only see a small fraction of what passes near us, and often we see it late. 3IATLAS, a relatively large and active object, gave us about 14 months between first detection and closest approach. That already feels tight. Now imagine something a bit smaller, dimmer, with less outgassing to announce its presence. Say a body around 100 or 150 meters across, coming in from near the Sun's direction. Perhaps, in that scenario, we would not notice until 3 weeks before its nearest pass. Astronomers would scramble to gather as many observations as possible, feeding the positions into computers that calculate possible orbits. Early on, those calculations might show a small but real chance of impact, 5%, perhaps, or something like it. Not a certainty, but not a number you can ignore, either. What do you do with knowledge like that? You cannot evacuate half a planet on a 5% probability. You cannot design and launch a deflection mission in 21 days. All you can really do is keep watching, keep refining the orbit, shrinking the uncertainty as much as physics and time allow, and share what you learn with the people who must decide how to respond. In the end, the path will resolve one way or another. The object will miss, as most do, or it will not. Either way, the scenario itself is not imaginary. It sits quietly at the edge of what our current surveys and models tell us is possible, a reminder that in this vast, busy galaxy, we are still just beginning to learn how to see what moves toward us in the dark. When you let all of this settle, another quiet detail emerges that makes the whole picture feel even more fragile. Almost everything we've practiced for, in our early attempts at planetary defense, assumes a particular kind of threat, near-Earth asteroids drifting along at 10 to maybe 25 kilometers per second, moving in orbits we can trace and project years into the future. Interstellar visitors live in a different lane. They can rush in at 30, 40, even 50 kilometers per second relative to Earth. At those speeds, every extra kilometer per second steals a little more of our reaction time and makes any attempt to nudge them that much harder. It's as if the galaxy occasionally drops packages on our doorstep that we never ordered, with no tracking number, no delivery window, and no way to know what's inside until they're already close. 3IATLAS happens to be one of the rare boxes we saw early enough to open gently with telescopes and equations. But the statistics whisper that there are others out there right now, some smaller, some perhaps closer, sliding past unnoticed simply because they are faint, fast, or approaching from directions we barely watch. That realization leads, almost inevitably, to a question that's both simple and heavy. What are the actual odds that something truly dangerous is on its way toward us? Not in a story, not in a movie, but in the quiet arithmetic of real risk. And how does that risk sit beside all the other big worries we carry as a species? To begin anywhere honest, we have to talk about numbers, not headlines. For decades, NASA's Near-Earth Object Program has not only cataloged asteroids, but also tried to weigh their danger through a single measure that blends two ingredients: how likely an impact is and how much energy it would release. On that scale, anything above a certain threshold is flagged for careful watching. A value above 0 means the threat stands out from the usual background of similar-sized objects that buzz harmlessly by. Right now, looking ahead about a century, there are no known asteroids with a score above that 0 line. None that, based on what we can see today, pose a special, named risk. That does not mean the danger is gone forever. It just means that, among the large objects we already know about, none are currently on a path that crosses ours at the same time. Geology gives us a longer, quieter view. The impact that ended the age of the dinosaurs, driven by an object around 10 kilometers across, was not an everyday event. Craters scattered across Earth's crust suggest that collisions of that size happen only once every 100 million years or so, give or take a long stretch. The last one was about 66 million years ago. Statistically, on those timescales, we are not due for another in any human sense of the word. Smaller impacts, though, are more frequent. An object tens of meters wide exploded high over Siberia in 1908, flattening forests across thousands of square kilometers. Events of that rough scale are thought to occur every few centuries. The Chelyabinsk meteor in 2013, about 20 meters across, arrived with little warning and injured thousands with its shockwave and shattered glass. Happenings like that are expected perhaps once in a human lifetime. Tiny meteors, the sort that quietly burn up in the upper air as shooting stars, arrive by the thousands each day. Over the past few decades, we have become quite good at tracking the biggest, most worrisome native asteroids, especially those larger than a kilometer across. We think we've found the vast majority of the ones whose orbits come near Earth. The remaining unknowns at that size are likely on paths that do not intersect our own, or they would have shown themselves by now. From that perspective, the risk of a civilization-ending impact from a long-period, homegrown asteroid in the next few centuries looks reassuringly low. Interstellar objects, however, sit off to the side of that comfort. The odds quoted above are built on populations we can count and paths we can follow. Visitors from other systems are, by their nature, random encounters. They are not woven into our predictive models because, until recently, we barely knew they existed at all, and we still do not know exactly how many pass through the inner solar system or how their paths are distributed. Even so, people who think about these things have tried to sketch an estimate, using the rate at which we've discovered Oumuamua, 2I, Borisov, and 3IATLAS, and correcting for how narrow our observational net still is. Some studies suggest that an interstellar object more than 100 meters across may pass inside Earth's orbit about once a year on average. Most of those bodies will miss us by wide margins. Space is big, and Earth is a very small target. But when you extend that low yearly chance across millions of years, the numbers hint that, sooner or later, one such object will wander along the wrong line at the wrong time. Very rough calculations, draped in wide error bars, and honest humility put the time scale for a region-devastating impact from an interstellar visitor somewhere between 10 million and 100 million years. That is a long, soft horizon, similar to the rate for dinosaur scale hits from our own solar system, but with an important twist. For the local objects, we can hope to see the danger decades ahead of time. For the visitors, our warning might be measured in months or weeks. One astronomer once framed it this way: in any given year, the chance of a large interstellar impact is vanishingly small, but so is the chance that, if one did come, we would spot it with enough time to do anything about it. The risk is a double-edged thing, tiny in likelihood, enormous in consequence, and coupled to very limited preparation time. Set that beside the other shadows we live with, and the picture becomes more nuanced. Climate change is not a distant possibility. It is unfolding now, in decades that span our own lives. Pandemics, as we have all seen, can rise from the background of ordinary life and sweep around the world in a year, changing economies, habits, and histories. Nuclear weapons exist in stockpiles we can count. Their use is unlikely on any given day, but entirely within human power. Debates about artificial intelligence circle questions of control, misuse, and unintended consequences, resting not on distant rocks, but on choices made in labs and boardrooms. Asteroid and comet impacts sit in a different corner of that map. The probability in any single human lifetime is low. The damage, if the wrong object appears on the wrong path, could be immense. And unlike most other existential risks, this one is completely indifferent to our intentions. We cannot negotiate with a piece of rock and ice. We cannot ask it to pause or reconsider. We can only see it, measure it, and, if we are ready in advance, try to move it slightly off course. That "if" is where planetary defense becomes quietly unique. Of all the great risks we talk about, it is one of the few that is, in principle, fully preventable with technology we either already have or can realistically build. The universe will send whatever it sends, but whether those deliveries become disasters is, at least partly, up to how prepared we are to meet them. Right now, the small group within NASA, tasked with thinking about these things, the Planetary Defense Coordination Office, works with a budget that, on paper, sounds large, but shrinks quickly in context. It is a sliver of a larger space agency budget, which is itself a sliver of national spending. By some rough breakdowns, it comes out to something like the cost of a few cups of coffee per person each year devoted to watching for and planning around threats from the sky. Against that, place what is at stake if, someday, a mission launched because of their work nudges a large asteroid just enough to miss. The benefit is not a new product or a short-term gain, but the quiet continuation of everything. 8 billion lives, and all the lives that would follow. Economists sometimes speak of expected value, the probability of an event multiplied by its cost or benefit. Even if the yearly chance of a catastrophe is a tiny fraction of a percent, when you multiply it by the weight of an entire planet's worth of future, the argument for modest, steady investment starts to look less like alarmism and more like simple care. And yet, as a species, we struggle with dangers that are both rare and enormous. Our minds are tuned to notice the sudden, nearby threat, the shadow in the grass, the wave on the shore, not to calmly weigh one in a million risks stretched over spans longer than our lives. Psychologists call this probability neglect, We overreact to vivid but unlikely fears, and we underreact to slow or abstract ones, especially when they have never happened to us before. There is a quiet irony in the fact that we, right now, may be the first generation in Earth's history that can even ask these questions seriously. For almost 4 billion years, life here had no say in whether a wandering rock ended an era. The great extinctions carved into the fossil record, whether by impacts, eruptions, or other upheavals, simply happened. Dinosaurs never had the chance to build telescopes or launch probes. They never got to argue over budgets for sky surveys. We do. We have already shown, with missions like DART, that we can alter an asteroid's motion, if only a little. Planned observatories like the NEO Surveyor promise to close many of the gaps in our watch, catching more of the small, dark objects that now slip by unseen. Piece by piece, we are assembling the tools that could, someday, turn a natural disaster into a near miss. What we have not yet done is treat those tools as something urgent enough to finish. We fund them modestly, fit them into schedules crowded with other priorities, and tell ourselves there will be time later to make the system more complete. The universe, of course, runs on no one's timetable but its own. So the question that lingers underneath all the numbers is not purely technical. It is philosophical and quietly moral. How much should we, living now, choose to spend to lower a risk that might not blossom into reality for thousands or millions of years? Is it wise to invest in defenses our grandchildren's grandchildren may never see used, or unwise not to, knowing that the clock on such events is long but inexorable? The rock that ended the dinosaurs' story did not ask their permission. If something similar appears on our horizon one day, we may be the only form of life this planet has ever hosted that is able to do anything about it. The choice before us is simple only in its outline: whether to build what we need before any countdown begins, or to trust, perhaps more than we should, that the sky will stay quiet without our help. As all of these ideas swirl together, there is still one very simple, very concrete clock quietly ticking in the background: the real night on the real calendar. December 19th is not an abstract date in a paper. It is a moment that is actually drawing nearer. On that night, while most of the world goes about its ordinary routines, a web of instruments on mountaintops and in orbit will be focused on a single moving point, doing their best to catch every photon 3IATLAS offers as it makes its closest pass. Hidden inside those patterns of light are hints that might, one day, help us face a visit that is not so harmless. Once that night has passed, the object itself will not linger. Its path is not a loop, but a one-way arc. After closest approach, the sun's gravity will bend its trajectory a little more and then release it, giving it a final sling. 3IATLAS will recede through the outer solar system like a stone rolling back up the walls of a well. It will cross the orbits of the giant planets, growing fainter with each month, until even our best telescopes can no longer pick it out from the background stars. Beyond the ice of the Kuiper Belt and the faint outer breeze of the heliosphere, it will slip back into the deep, thin dark between stars. Give it 10 years, and it will already be so far away that it becomes for us just numbers in an old file. Give it 100, and it will be light years from here. Give it thousands or millions of years, and it may wander close to another star entirely. There, perhaps, if that system also has curious eyes and quiet sensors, someone else might notice the faint intrusion of a small, fast-moving dot and ask their own version of the question we are asking now. What is this? And where did it come from? Follow that thought far enough, and 3IATLAS becomes less a single object and more a symbol, one of countless messengers drifting from system to system, each carrying a record of the place that made it. Most of those messages pass unread. They cross planetary orbits when no one is looking, or only when there is no one there to look. Only rarely does the timing line up, so that a world with tools and curiosity happens to be watching as one of these bottles in the cosmic ocean floats briefly past its shore. For the object itself, the story after December is simple. It travels on and slowly forgets us. For us, the story becomes richer and more tangled. The data gathered around closest approach will not be solved overnight. It will be pored over, checked, and rechecked by people who today might still be learning basic physics in a classroom. Entire theses will grow out of small corners of the dataset. One person focusing on how the brightness flickered as it spun, another on how its path bent under solar and planetary pulls, another on subtle shifts in its spectrum as it moved farther from the Sunday. Slowly, as those efforts accumulate, 3IATLAS will turn from a headline into a reference point. It will join Oumuamua and 2I Borisov as part of a small but growing family of interstellar visitors that we know not just by name but in some depth. That is where its real power lies. A single strange object can always be written off as an exception. Two can be compared, but leave you wondering whether you have found a pattern or just happened to catch two very different relatives. Three begin to outline a story. Our first visitor, Oumuamua, gave us an elongated shape, no visible coma, and a puzzling extra push on its way out. It was like meeting a guest who refuses to fit any familiar social category. Was it a comet with its gas all buried? A shard of something larger? A splinter of exotic ice? The second, 2I Borisov, felt more reassuring. It behaved like the comets we knew, a bright, obvious tail, abundant volatiles, a chemistry that said, "I am ordinary, just from somewhere colder." With it, we learned that at least some other systems make comet-like bodies very much as ours does. 3IATLAS seems to sit somewhere between those two tails. It wears a clear coma and lets off familiar gases, like Borisov, but its motion hides an extra acceleration that echoes Oumuamua's mystery. In its light, curves, and spectra, we see both the normal and the strange. That combination is scientifically precious. It suggests that interstellar object is not a single type of thing, but a whole spectrum of possibilities. Some very comet-like, some very odd, and many occupying the spaces in between. With 3 examples, we can start to sketch what that spectrum looks like. Planetary scientists like to say that every new class of object teaches you twice, once about itself and once about everything you thought you already understood. In this case, each interstellar visitor is also a lesson in how planetary systems form and evolve across the galaxy. When we unpack the gases in 3IATLAS's coma, we are really peeking into the chemistry of another star's nursery. When we track its spin and strength, we are really asking how sturdy the small building blocks of other systems are. That feeds directly into a question astronomy has been circling for decades. How typical is our solar system? We have now discovered thousands of exoplanets orbiting other stars. We can weigh some of them, estimate their sizes, and, in a few lucky cases, sniff their atmospheres. But they remain points of light far beyond our reach. We will never visit them. Interstellar objects are different. They are physical pieces of other environments that have wandered into our reach. offering themselves up to be studied in exquisite detail compared to anything else at those distances. You can think of each one as a tiny, uninvited, sample return mission. We did not pay to launch it. We cannot bring it into a lab, but we can let the sun's warmth coax its outer layers into vapor, and we can read that vapor with our instruments. Every spike and dip in its spectrum becomes a line and a quiet report about what kinds of ices and rocks foreign disks produce, how they weather in deep space, and what raw materials might be common across the galaxy. There is another, more practical layer to this too. Each time an interstellar object appears, we learn not just about its chemistry, but about our own ability to notice it. Oumuamua taught us how easy it is to recognize a visitor only when it is already on the way out. 2I Borisov helped refine the algorithms that distinguish a hyperbolic path from that of a long-period comet bound to our Sunday. 3IATLAS, seen earlier and watched more closely, will reveal new gaps and new strengths in our survey systems. In the very near future, a new set of eyes will join the effort. On a Chilean mountaintop, the Vera C. Rubin Observatory is preparing to begin a survey of the sky that will be deeper and more frequent than anything we have done before. Its wide, sharp gaze will scan the entire visible sky every few nights, catching transients and movers that would have slipped by unnoticed in older datasets. Many astronomers expect that once it is fully up and running, the rate at which we discover interstellar objects will jump. Instead of a handful per decade, we might find one every year, or even more. If that happens, 3IATLAS will be remembered as part of the opening chapter of a richer era. Dozens of visitors would give us not just isolated curiosities, but statistics. We could look for patterns in their sizes, their speeds, their directions. We might find that many share similar compositions, hinting at common birthplaces, or that some come in clumps from certain patches of sky, suggesting streams of debris from long disrupted systems. With precise enough tracking, we might even trace a few back, in reverse, to likely home stars, turning nameless rocks into labeled samples from specific suns. Ideas that feel barely possible now, like sending a spacecraft to meet one of these wanderers up close, become more realistic too. Once we know they are not once-in-a-lifetime opportunities, but recurring chances. Engineers have already sketched mission concepts that would use clever gravitational assists and fast trajectories to chase down a visitor detected years in advance. The technical hurdles are steep, but not unimaginable. A probe that could fly alongside an interstellar object, map its surface, taste its dust, maybe even grab a tiny piece to bring home, would change this quiet, remote kind of science into something visceral. While those possibilities belong mostly to the future, there is a more immediate kind of meeting that happens every time a story like 3IATLAS enters the public conversation. News articles, videos, and posts ripple outward. Some of them exaggerate, some speculate, some drift quickly into talk of alien ships and secret messages. It is easy for scientists to sigh at that, but hidden inside the noise is something precious, genuine curiosity. People who might never have thought about comets or orbital mechanics before find themselves wondering about an object from another star sweeping past our world. If that curiosity is met with clear, patient explanations, with invitations to look through a telescope, to download a star chart, to watch a live stream of data coming in, it can become more than a passing thrill. Teachers can build lessons around a real event unfolding in the sky. Amateur astronomers can contribute their own careful observations. Children lying in backyards or on apartment rooftops can imagine, maybe for the first time, that the universe is not just a backdrop, but a place we can understand and gently touch with our tools and questions. Each interstellar visitor, then, is not just a scientific gift, but a cultural one. It offers a rare opportunity for everyone on this small planet to think together about where we sit in the wider scheme of things, to feel for a moment both our vulnerability and our capability, small creatures on a fragile world who can nonetheless notice, measure, and begin to prepare. And beneath all the math and engineering, beneath the budget lines and mission concepts, there is a softer layer that is harder to quantify, but just as real. Objects like 3IATLAS quietly invite us to decide what kind of species we want to be. One that drifts from day to day, hoping the sky stays kind, or one that chooses to look up, to plan ahead, and to care about futures far beyond the span of a single lifetime. Somewhere in that choice lies a question that doesn't fit neatly into any equation, a question about responsibility, about wonder, and about how seriously we take our brief time here under the stars. It is the kind of question that doesn't demand an immediate answer, but rather asks to be kept close, turned over slowly, and sat with for a while in the gentle quiet of the night. What does it really mean to live in a universe where pieces of other star systems can drift through our sky? For most of our story as a species, we imagined our home as a closed little system, one sun, a handful of planets, some moons and comets and belts of rock, all part of the same original family. Other stars were there, of course, but they were so far away that they felt like decorations on the ceiling of a room we would never leave. There was us, and there was everything else, with a clean line between them. The discovery of Oumuamua in 2017 quietly erased that line. Suddenly, it was no longer just an idea that material from other systems existed somewhere out there. A shard from another neighborhood had actually flown right through ours. 2 years later, 2I, Borisov, did it again, this time wearing a clear comet's tail. And now, 3IATLAS is adding its own strange signature to the list. 3 visitors in less than a decade is not a fluke. It's a hint that this kind of crossing is normal, that the galaxy is not made of sealed-off islands, but of systems that slowly trade material over immense spans of time. On a human level, that realization changes the feeling of the night sky. Every generation before us looked up and saw unreachable points of light. You, living now, are part of the first generation that knows, with direct evidence, that bits of those distant systems can actually make the journey here. The cosmic neighborhood you were taught about as a child, one star, a small family of worlds, has quietly expanded into something wider. When you think of here now, it can mean not just the solar system you were born into, but a place that passing visitors from other suns occasionally thread their way through. Even if you never see one directly, the knowledge that they exist folds into the way you picture the world, like a new room you've discovered in a house you thought you already knew. Those visitors are not young. 3IATLAS could be older than the Earth itself. It might have formed around some distant star 5 billion years ago, when our sun was still just a knot of gas in a larger cloud. The star that shaped it could, by now, have swollen into a red giant or faded into a white dwarf. That whole planetary system might have changed beyond recognition, or even been stripped of worlds in some ancient gravitational shuffle. Yet this one small fragment endures, carrying in its ices and dust a record of conditions in a place that may no longer exist in any familiar way. It is, in a gentle sense, a fossil from a lost landscape, drifting on long after its home has gone. When you see an image of 3IATLAS, or read the spectra taken from its coma, you are looking at deep time made almost touchable. The atoms in its iron, its carbon, its oxygen were forged in explosions and interiors of stars that never had anything to do with our own Sunday. Carl Sagan's quiet reminder that we are made of star stuff turns out to have an extra layer. There is star stuff from other stellar families passing right through our cosmic front yard. The story of matter in the galaxy is not just a loop within one system. It's a long, wandering exchange, with elements passing from star to planet to debris and back into clouds that may one day form new suns. That has gentle but profound implications for questions about life. For a long time, the idea that life, or at least its basic ingredients, could travel between star systems was treated with a kind of skeptical fondness. It had a name, panspermia, and it mostly lived at the edge of serious discussion. Now, we know that solid bodies really do roam between stars, that some of them are rich in organic molecules, and that hardy microbes can survive for a while. The vacuum and radiation of space, if shielded inside rock or ice, none of that proves that life on Earth came from elsewhere, but it does make the possibility less fanciful. It turns an old, speculative story into something that, while still unproven, at least fits inside the boundaries of what physics and chemistry allow. Even if life here grew entirely from local seeds, the principle holds. Our star is not an isolated garden. Over billions of years, dust and rock and ice from other systems have likely crossed our orbit again and again, some burning up in the atmosphere, some landing in the oceans or the soil, some passing by without us ever noticing. In the other direction, fragments thrown out of our own family pieces blasted off. Mars, the Moon, or even Earth have probably drifted outward as well, joining the slow, sparse traffic of the galaxy. We live not in a sealed room, but in a neighborhood with a very low but real exchange of material. What happens around one star can, given enough time and enough wandering debris, leave its faint fingerprints around another. Bring that knowing back down to something as ordinary as a date on a calendar. On December 19th, 2025, 3IATLAS will be making its nearest pass. Most people will go about their routines. Many will never hear its name. Somewhere, though a few thousand meters above sea level, domes will be open and instruments humming. On screens, in control rooms and laptops, in quiet offices, small moving points of light will be traced and measured. Behind those points is the simple fact that, for the first time in history, we can watch in real time as a visitor from another star brushes past our world, knowing what it is and what it means. You don't have to see it with your own eyes for that to matter. Just knowing it is there, knowing that above you, a half-kilometer of ancient ice and rock from a distant system is threading its way through the inner solar system can be enough. For a few hours, that lonely traveler will be as close to us as it will ever come in all its long existence. It has spent millions of years in cold so deep that winter is too warm a word. Now, for a brief moment, it is close enough for sunlight to wake its surface, close enough for our instruments to read what it whispers back. Then it will slip away again, its path bending slowly outward toward the dark. The scientists watching will be doing what they always do, turning faint signals into understanding. They will use 3IATLAS to refine models of how planets form, how small bodies are flung out of young systems, how interstellar space slowly alters ice and rock. They will test survey software and detection pipelines, learning how to spot the next visitor a little earlier, measure its path a little more precisely. Some of them, quietly, will also be thinking about planetary defense. about what it would take to protect this world if an object on a different trajectory ever came a little too close. For them, this is both a scientific gift and a rehearsal. All of that careful work is part of a larger, slower pattern. After December 19th, telescopes will turn elsewhere, but the data will remain. Over the years that follow, 3IATLAS will show up again and again in plots and papers, each time revealing something slightly different, a nuance in its chemistry, a subtle clue in its motion. It will join Oumuamua and 2I Borisov as one more marker in the emerging map of how material moves between stars. As new interstellar objects are discovered, they will be compared to this small first family, and slowly the scatter of points will begin to look like a pattern rather than a handful of isolated curiosities. Meanwhile, survey telescopes will grow more sensitive, new observatories will come online, algorithms will improve. Instead of hearing about one interstellar object every few years, we may start hearing about them regularly, first as small notes from astronomers, then as occasional ripples in the news. Each one will carry its own personality, some brighter, some darker, some more active, some stubbornly quiet. A few may be discovered early enough and move slowly enough that people can seriously talk about sending a spacecraft to meet them on purpose, not as a desperate measure, but as a planned visit. By then, the idea that other star systems can visit us may feel less startling and more like part of the quiet background of how we think about the galaxy. We will talk about samples from particular regions of the Milky Way, about families of interstellar comets that share certain traits, about captured objects that now live full-time in our sun's care. The picture of our place here will shift from a solitary system out on its own to one node in a vast, thin web of exchanged matter and shared history. In that picture, the Earth is not the center of anything, but it is also not as alone as it once seemed. For you, though, it can also stay simple. On that December night, or on any night when your thoughts drift outward, you can let yourself remember that we are living through a set of firsts. First confirmed interstellar visitors, first tested methods of nudging asteroids, first serious plans to one day chase down a wanderer from another sun. Our ancestors looked up with stories of gods and omens. We look up with equations and simulations, but underneath both is the same feeling, wonder, mixed with a small, sharp awareness of how fragile our world is, how easily it might have been otherwise. 3IATLAS holds both sides of that feeling at once. It is a source of beauty, a quiet, passing proof that the galaxy is alive with motion, and a reminder that the universe is not arranged for our safety. The same processes that gently deliver samples from other systems can, on long enough timescales, send us real threats. Learning to see those threats in time and to do something about them is part of what it means to grow up as a spacefaring species, even if we are only at the very beginning of that path. After December 19th, life here will go on. Morning will come. The headlines will move on to other things. The visitor will shrink back into the dark and then into invisibility. Yet the questions it raises will stay. How many more are there? How much can we learn from them? How far are we willing to go to be ready, not just curious? Those are not questions with quick, neat answers. They are the kind you carry with you for years. There is a quiet comfort in knowing that we do not have to answer all of that tonight. For now, it is enough to know that somewhere above you, on that marked date, a messenger from another star will be racing past, carrying stories written in chemistry and motion instead of words. It will leave us nothing we can hold, but much that we can think about. If you close your eyes for a moment and picture it, You are already taking part in the small, shared act of attention that makes discoveries like this matter. We are living in an age when the universe does not just sit at a distance, but reaches in, now and then, with small, solid reminders that we are part of a much larger conversation. 3IATLAS is one such reminder. Notice it, if only in thought. Let it widen your sense of here just a little. And when it is finally gone into the dark, remember that space between stars is not empty. Somewhere, out beyond the edge of our sight, the next visitor is already on its way.